Why do apples fall down instead of up? This simple question has led to centuries of scientific investigation and debate. It's a puzzle that starts with something as mundane as an apple and spirals out into the cosmos, shaping the universe and our place within it. This unseen force, which we call gravity, is central to our existence, yet its true nature remains enigmatic. Join us as we traverse through time and explore the top 10 theories about the nature of gravity. Our journey begins with Aristotle, who believed in the concept of natural place. Aristotle's theory was simple yet profound. He proposed that every object yearns to reach its natural place in the universe. To Aristotle, the earth was the center of it all, the natural place for all earthly objects. And so, he argued that these objects, when in motion, would always seek to return to the earth. But Aristotle didn't stop there. He also suggested that heavier objects fall faster than lighter ones. Imagine dropping a feather and a stone from the same height. According to Aristotle, the stone being heavier would reach the ground first. It was a theory that seemed to make sense, and for centuries it was largely accepted. But this theory would soon be challenged, leading to a revolutionary new understanding of gravity. The stage was set for the next protagonist in our story of gravity, and his name was Galileo Galilei. Galileo Galilei, with his iconic Leaning Tower of Pisa experiment, debunked Aristotle's theory. Ever heard of it? Galileo, in his rebellious spirit, questioned Aristotle's claim that heavier objects fall faster than lighter ones. He put this theory to test at the Tower of Pisa, dropping two balls of different masses. What happened next was groundbreaking. Both balls hit the ground at the same time. This was a direct contradiction to Aristotle's theory. What Galileo revealed was that all objects, regardless of their mass, fall at the same rate in a vacuum. This was not just a simple experiment, but a revolutionary concept that challenged the established beliefs of the time. It's fascinating, isn't it? How one experiment, one idea, could change our understanding of the world. Galileo's discovery was a pivotal moment in scientific history that gave us a fresh perspective on gravity. This paradigm shift set the stage for the genius of Sir Isaac Newton. In the 17th century, Sir Isaac Newton proposed the law of universal gravitation, forever changing our understanding of the cosmos. This law holds that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This means that the further apart objects are, the weaker the gravitational pull between them. Newton's law of universal gravitation was groundbreaking. It provided a unified explanation for the motion of celestial bodies, from the fall of an apple to the orbit of the planets. With this law, the same set of rules applied to the heavens and the earth, eliminating the need for separate terrestrial and celestial physics. The law also explained the tides and the precession of the equinoxes, phenomena that had puzzled scientists for centuries. It was a powerful tool for predicting the movements of the planets and stars, and it laid the groundwork for our current understanding of the universe. However, despite its success, this law was not without its flaws. It could not explain the anomalous precession of the planet Mercury, a problem that would puzzle scientists for centuries. Furthermore, Newton's theory was unable to reconcile the force of gravity with the principles of quantum mechanics, leading to a search for a more comprehensive theory. But even Newton's law had its limits, which were later exposed by the genius of Albert Einstein. If you're enjoying our journey through the enigmatic world of gravity, don't forget to hit the subscribe button below for more such enlightening content. It's your support that keeps us going. And if you're finding this video interesting, do give us a like. Your thumbs up motivates us to delve deeper into the mysteries of the cosmos. We would also love to hear your thoughts and theories about gravity. So don't hesitate to leave a comment below. We read every single one of them. Now, let's dive back into our exploration of gravity as we unravel the revolutionary theory of a man named Albert Einstein. Stay tuned. Albert Einstein, in the early 20th century, proposed a groundbreaking theory that redefined gravity. Imagine you're on a trampoline. When you jump, you create a depression in the fabric. That's a bit like how mass and energy work in Einstein's general theory of relativity. But instead of a trampoline, we're talking about the fabric of space-time, the four-dimensional stage upon which all events in the universe play out. Einstein suggested that mass and energy tell space-time how to curve, and in turn, curved space-time tells mass and energy how to move. This is a radical departure from Newton's gravity, which saw gravity as a force acting between two bodies. In Einstein's view, gravity isn't a force that pulls objects towards one another. It's the shape of space-time itself that guides their motion. Think of a planet orbiting a star. The star's mass warps space-time around it. The planet, moving along this curved space-time, appears to us as if it's being pulled in by the star's gravity. But it's actually just following the simplest path, a geodesic, in the curved space-time around the star. One of the most stunning confirmations of Einstein's theory came during a total solar eclipse in 1919. Observations during the eclipse showed that the light from stars passing close to the sun was bent, appearing in slightly different positions than expected. This bending of light, or gravitational lensing, was a direct prediction of Einstein's theory. So, why does this matter? Well, without Einstein's theory, GPS systems wouldn't work correctly. We wouldn't understand the behavior of black holes, and we couldn't comprehend the expansion of the universe. Einstein's theory holds up to this day, but the quest to understand gravity doesn't end here. This is the fascinating story of gravity, a story that has been unfolding for centuries and one that continues to be written. The next chapter, quantum gravity. But that's a tale for another scene. The world of quantum mechanics shook the foundations of physics, and with it, our understanding of gravity. Quantum mechanics, rules that govern the smallest particles of the universe, has always been at odds with gravity. While Einstein's theory of general relativity paints a vivid picture of how gravity curves the fabric of space and time, quantum mechanics describes a world of randomness and uncertainty at the microscopic level. These two theories, despite their respective successes, are like oil and water. They simply don't mix. This has led scientists on a quest to reconcile these two theories. Enter the realm of quantum gravity, a theoretical framework that attempts to unify the gravity of general relativity with the quantum world. The most promising candidate for this unification is string theory, which postulates that all particles are tiny vibrating strings. In string theory, gravity emerges naturally as the strings vibrate in multiple dimensions. This theory, while still in its infancy, has the potential to revolutionize our understanding of the universe. It could potentially explain the Big Bang, the formation of galaxies, even the nature of black holes. Yet, despite the promise of quantum gravity and string theory, we are still a long way from understanding the true nature of gravity. These theories remain untested, unverified, and thus in the realm of speculation. Despite the breakthroughs, the nature of gravity remains one of the greatest unsolved mysteries in physics. As we gaze into the future, the mystery of gravity continues to captivate scientists worldwide. The quest to understand gravity is a journey that carries us across the threshold of the known universe into the frontiers of the unknown. The field of gravity research is vibrant and dynamic, with scientists around the globe tirelessly striving to unravel its intricacies. One of the most promising areas of research is gravitational waves. These ripples in space-time, first predicted by Albert Einstein, were finally detected in 2016. They provide a new way to observe the universe, potentially offering insights into phenomena such as black holes and neutron stars. Another exciting frontier is dark matter. This elusive substance, which makes up about 80% of the matter in the universe, interacts with gravity in a way we don't yet fully understand. In the future, experiments designed to detect dark matter could illuminate new aspects of gravity's nature. And let's not forget the holy grail of physics, the unification of gravity with quantum mechanics. This would reconcile the macroscopic world of general relativity with the microscopic world of quantum physics. Quantum gravity, if achieved, would revolutionize our understanding of the universe. The future of gravity research is as boundless as the universe itself. Each day brings new questions, new theories, and new possibilities. Who knows what new insights and breakthroughs await us in our quest to unravel the enigma of gravity? From Aristotle to quantum mechanics, the journey to understand gravity has been a long and fascinating one. We have traveled through time, from ancient Greece, where Aristotle believed objects sought their natural place, to the Renaissance era, where Galileo debunked this theory with his law of equal fall. We then ventured into the Age of Enlightenment, exploring Newton's universal law of gravitation and how it laid the foundation for our modern understanding of the cosmos. From there, we delved into the 20th century, where Einstein's general theory of relativity reshaped our understanding of gravity as a curvature of space-time. In our quest for understanding, we've also explored the enigmatic world of quantum gravity and the attempts to reconcile it with the macroscopic world. The future of gravity research promises to be just as exciting and unpredictable. While we may not yet fully understand gravity, its mysteries continue to inspire and drive scientific exploration. Who knows, perhaps you might be the one to finally solve the puzzle.